Good morning, students. Today we are going to explore Deuteron problem. Before that, why Deuteron is a problem or why it is a matter to study. First of all, in cell model, we have seen that there are cell structure. There are evidences that there are cell structures inside the nucleus, and the cell closure is similar. Those that can explain the existence of magic number and magic number nuclei are stable nuclei. And in cell model, using the conceptions of the cell model, spin and magnetic moment of the nuclear, most of the nuclei were predicted, which agreed with the experimental value to some experimental application within some experimental application. The nature of the interaction between the nucleons were assumed to be harmonic oscillator potential. That means not the interaction, but a single nucleon is moving inside the nucleus. The potential is assumed to be harmonic oscillator. Now, our aim is to explore the nature of nuclear interaction. That means the nuclear is strong force by which protons, in spite of tremendous amount of repulsive forces due to Coulomb interaction, how the protons are packed in a very small region. So strong nuclear force, the existence of strong nuclear force was postulated, and the strength of the strong nuclear force must be very high, and of course this must be very short range. If it is not short range, then the alpha radioactivity would not have been observed. In order to investigate or find the nature of interactions between the nucleons, between that means between proton proton and between neutron neutron, the simple atom or the first nuclei, the simple nuclei or the first nuclei to be investigated is a deuteron. Because in deuteron there is one proton and there is one neutron which can interact among themselves with strong nuclear force. The lightest element is hydrogen, but in hydrogen, in the nucleus only proton, so there is no other nucleon to interact. So the lightest nuclei, the lightest isotope, which can be taken for investigating the nature of strong nuclear force, is the deuterium. That's why deuterium is taken. Right? And we have named this deuterium problem. What are the experimental evidences that we are getting from deuterium? And then we will proceed in two approaches. One is bound state, deuterium is a bound state, and then we will also see that in case of NP scattering, that means proton is fixed and by neutron we are bombarding it. By the study of the scattering cross section, which is a free state problem, scattering is of course a free state problem. So by scattering problem, we will also investigate the nature of strong nuclear. force. But first, we investigate the strong nuclear force or the nature of the nuclear force with bound system. And the lightest bound system is the Deuterium. So let us see what we find or for the Deuterium experimented. First one, the binding energy 2.2245 MeV. You can this can be calculated very accurately, knowing the mass of the deuterium, and you know the mass of the proton and the mass of the neutron. Add up the mass of the proton and mass of the neutron, and it will be greater than the mass of the deuterium. The difference in mass has to be converted delta m into energy by the relation delta m c square, and that energy is 2.2245 MeV. So binding energy per nucleon, we divide it by 2, there are 2 number of nucleons there. So it will be 1.112, which is much smaller than the average value 80 MeV for other nuclei. Right? You have seen in your UG classes that the binding energy per nucleon has a curve, binding energy curve, the famous curve, which is peaked at iron. First it is increasing with the atomic number, then it is peaked at iron, then it is decreasing that number. Okay? Uh, Curvature like this. Okay, that's the curvature for no sorry, the binding energy per nucleon has a curvature like this. First it is increasing with the atomic number, peak at iron, and then it will decrease. And the highest value or the average value for the binding energy per nucleon is 80 MeV. Right? For alpha particle, that means for helium nucleus, binding energy per nucleon is 7.07 MeV. But in case of deuterium, binding energy is 1.1122 MeV, which is much smaller than average value. So we can say that at once the deuterium is a rather loosely bound. So by comparing the binding energy of the deuterium, we can say that the deuterium is a very loosely bound state in compared to the other heavy mass number or heavy atomic number. The spin of the deuterium is 1. Experimentally, spin of nuclei can be measured. Now, spin of the deuterium is found to be 1. Now, we have now cell model. Using the same model, one number of proton and one number of neutron. So, both have spin half, right? Angular momentum, total angular momentum J will be half. So, both will be in 1s half. So, spin of neutron and proton will be half, and if it is adding up vectorially or the spin are in parallel, then it may be 1. We'll see that why it is spin is 1. So I'm moving to the next slide. Other experimentally measured magnetic moment of the Deuteron. Magnetic moment can be measured, you know. Its magnetic moment is 0.857417 mu n. Mu n is the nuclear length. Deuteron possesses small but finite quadruple moment. It has a quadruple moment, not very large because there is a sign 10 to the power minus 31. And the parity of the Deuterium downstate is given. That means either L value is the L value is are given. That means L will be equal to 0 or 2 or 4 or it is. So these are the experimental evidences that we obtain. Now we analyze uh, how these experimental values, especially the first one has been explained, second and third value. We are considering now the second and third value, the third experimental evidences for the Deutsche. Now, from the observational fact that neutron and proton have half integral spin. If the spin are aligned parallel, then the resultant spin would be 1. And this is also consistent because we know magnetic moment of proton and magnetic moment of neutron, intrinsic spin magnetic moment of the proton and neutron have been determined. No intrinsic spin magnetic moment for proton and neutron. For proton it is 2.7927 UN and for neutron it is minus 1.917 UN. And since neutron, the magnetic moment for neutron was negative, if we add up these two things, then this comes out to be 0.8796 nu n, which is very close to the experimental value that we have obtained. Experimental value is 0.85, 0.857417 and theoretical value of it is 0.8796. So this matches. So from point number 2 of the experimental fact, we can say 2 and 3 that the spin of the proton and neutron must have to be aligned parallel so that two half spins will give one spin. And the magnetic moments, one is positive and another is negative. Then if we add up algebraically, then magnetic moment also matches the experimental value. This figure depicts the spins. The first one is the spin of proton, second one is spin of neutron. These are parallel. These two spins are added up. Then ID. This will be twice the length of ID will be twice the length of SPN because spin is 1. And this is the magnetic moment for UP. Magnetic moment will be aligned along the direction of spin. And for SN, magnetic moment is opposite direction because of the structure of the neutron. Neutron, the neutron is supposed to be consist of a positive charge inside and a negative electron outside. So intrinsic magnetic moment is negative, and if we subtract this from this or add, since this is in opposite direction, if we add these two things, then mu d magnetic moment of approximately 1 because this is 2.7, this is 1.9, so this is approximately 3, this is approximately 2, and if we subtract this thing, then we approximately equals to 1. So the spin of proton neutrons are parallel and magnetic moments add up vectorial. So this we can say. Now till now we have not considered the angular momentum. We have only added up spin, but we have seen that in cell model the total spin must be found. Total spin J is found by coupling spin and orbit interest. Right? So if there are orbital motion, of course there should be orbital motion because the protons and neutrons are in motion. Now if you consider the orbital motion and the coupling of spin and orbital motion, then how we can explain this? Now we are coming to this. Angular momentum L must be added vectorially spin Deuterium. So the Deuterium has spin 1. So in order to obtain spin, the spin are parallel. Spin are parallel. So spin of the Deuterium is 1 from cell model. And experimental value is also 1. Then if for L equal to 0, this is the case. Now if you consider L equal to 1, so for L equal to 1 is spin is this. For magnetic spin angular momentum is this. For increasing spin this. So total angular momentum this plus this will be, so this forms an equilateral triangle, right? So for L equals to 2, this can also be done. That a spin equals to 1, their spins are parallel. Spin equals to 1, spins adds up, and that spin also adds up with the resultant orbital motion and gives you total angular momentum I equal to 1, J equal to 1. And for L equal to 2, this is also possible. Say for L equal to 2, it is 2 unit. So SD equal to 1 and it is acting oppositely, then you will also get height equal to 0. So for L equal to 0, 1, 2 and for parallel spin of neutron and proton, 3 are the possible values of L. So L equal to 0 is possible, L equal to 1 is possible, L equal to 2 is possible. Again I repeat it, we have seen that spin of the deuterium is 1. Now if you add spins into the spins of the neutron and proton, then this is equals to 1. They are parallel. Now if you consider the orbital motion also will be there. Then for 3 orbital quantum number L equal to 0, L equal to 1 and L equal to 2, the spin state of the deuterium 1 is achievable. Get the point? Now while we will discuss it in the later more extensively, we will see that L equal to 1 and L equal to 2 states are not bound state for deuterium. So only bound state for deuterium is L equal to 0. We will see here. Now these are the values. Based on the experimental values, we can have these ideas without further detail, further investigation into the detail of the problem. Just from the experimental fact and the data that neutrons and protons have half increasing spin, we can say that these protons and neutrons spin are aligned parallel. Their magnetic spin is 1, their magnetic moment also matches. And for 3 values of L, spin 1 of deuterium is possible. L equal to 0, L equals to 1, L equals to 2. Now, since it is a bound state, now we have to solve it using Schrodinger equation. Right? For subatomic particles, we know we have to consider Schrodinger equation. Now, for Schrodinger equation for a two particle system, now next Schrodinger equation for a two particle system, center of mass system. C system means center of mass system. It will be like this. This is the Schrodinger equation where m is replaced by mu. Mu is given by mp mn by mp plus mn equal to m by 2, where we are assuming mn equal to mp equals to m, because their masses are so close to each other. We are assuming for the sake of simplicity that their masses are same and m. So for a single for when in case of cell model, this was only m. Now in case of this was only m, mu was replaced by m. Now in case of Deuteron, we have m equals to m by 2, right? The same equation is there. Now we have to consider the potential, right? There in cell model we have considered the potential of harmonic oscillator. Now here, since the two nucleons are only there, one is proton and one is neutron. So here the potential is the form of strong nuclear force. The many types of strong nuclear force have been suggested. Say for example, nuclear type, exponential type, harmonic oscillator type, but the potential which satisfies most of the experimental evidences is of the form rectangular type. And another reason for assuming rectangular type is that it is a very simple type, so that the solution of the Schrodinger equation will be easy. So we are taking the potential, that means potential due to strong nuclear force between the nucleons, to be square wave type, rectangular type. That means V equals to minus V0 for 0 less than r less than b. That means up to the distance b, the width of the well is b, and outside the b and outside b it is 0, right? So the potential will be of the form, this potential form of the potential we have showed the problem. And it is minus v0, potential is v0. Why it is minus? Because the force is attractive. For repulsive force, potential must be positive. For attractive force, potential is negative. So if negative potential of square wave type, that is rectangular type also, square is a form of rectangle, special form, equal to minus v0. If you substitute this thing, then the equation will be v equals to, there will be two regions, right? One is inside the potential and another will be outside the potential. Now what we have to do, we have to separate these out, radial part and angular part. Now as you have assumed in the cell model, that if we consider spherical symmetry, the angular part can be separated out and their solution is known. You know, spherical harmonics are the solution, and we are only interested in the radial part. So next, what we will do, as in the case of cell model, say the total wave function, that means solution of this equation. Solution of this equation, right? That means solution of this equation. The solution of this equation, this side is taken as angular part, product of angular part and radial part, and this is taken of this form. This is the usual form, this is YLM, this spherical harmonics, and ULR is the radial part, ULR by R is the standard form, radial part. Summation over L implies L equal to 0, 1, 2, 3, this kind of thing. While in the YM is the spherical harmonics, which are the solutions of the angular part. Theta as well as phi dependence has been observed out. Now, Since L is the angular momentum, right? You know YLM when it acts with the wave function, then it will give L into L plus 1 h car. And when we substitute this thing, the equation, radial equation has this form. You know, this equation was also the equation of cell model. Only is that the mu was given by m and other were the same. And the last term, L into L plus 1 by r square, this is centrifugal potential. This was also there for central force problem when we studied classical mechanics, central force problem. So this is a general character of the force. Now, for ground state, we are interested for ground state source. Then we will discuss L equal to 1, L equal to 2 later. But for the time being, for the sake of simplicity, we are considering the ground state. That means L equals to 0 means if L equals to 0, the centrifugal term has only the value of L equal to 0, this centrifugal term vanishes. This centrifugal potential, you can call it potential because it is adding up with the energy and potential. Yeah, kind. So it has the dimension of energy. This is called centrifugal potential. Right? Now this term vanishes for L equals to 0. So as I have said, there are two regions. One is inside the potential and another is outside the potential. So the two regions separated out like this. d2u in dr square plus twice mu s plus square e plus v0. There is a minus sign, but v0 is negative. So this v0 negative sign is taken. Negative sign is taken. So this is the equation. Schrodinger equation, radial part of the Schrodinger equation inside the strong nuclear potential, and of course outside the potential area, since V equal to 0, potential energy is 0. This is the Schrodinger radial part of the Schrodinger equation outside the nucleus. Now, since these two equations also you obtain when in scattering problems also, because these are general, right? But now we are considering bound state. That means the energy, any bound state should have total energy negative. You understand the point? Bound means it is bound. It is attached to something, and it has a energy negative. Why it has energy negative? Because to make it free, some additional energy from outside has to be imparted or inserted in it to make it free. So always, whether it is gravitational, whether it is electromagnetic, or whether it is strong nuclear force. Now we are considering strong nuclear force. Any bound state has a energy negative. Now we have seen that deuterium has a negative binding energy of 2.2 MV. So binding energy E equals to minus ED, right? So for bound state, where we are putting E equals to minus ED. Then this constant is K1 square and this constant is minus alpha square. This constant gives you minus alpha square. And we have taken K0 square to be this in the special case when E equals to 0. Right? For just bound state, which is neither bound nor free, or the intermediate state, just bound state we call it equal to 0. So these are three constants. Now inserting these three constants, the equations, mm, these two equations, inner region and outer region, I am going very slowly so that you can copy these equations in your copy while watching the video. So these two equations uh, reads out like this: d2ue dr square dr2 plus k1 square u plus d2 out dr square minus alpha square equal to 0, right? So this one this is constant is positive, here this is negative. So you know it has a solution exponential. This must be exponentially decreasing solution, and this will be sine of constant. You know these forms are known to you, very, very much known to you, right? Now, solution of these equations has the form I have written extensively for not only sign form of the first form, and from the boundary conditions, there are four constants a dash, b and b dash will be explained, right? Since the constant value of it will plus minus alpha, second equation, so it will be b exponential minus alpha plus b dash exponential plus alpha, right? These two equations. Now, since and the first equation equal to a sin k1r plus a dash cos k. Now, from the boundary conditions, we have to eliminate two constants from the four constants. Right? There are so because there are two equations, so two constants are allowed. Right? And given k1 and alpha are measurable or derivable, or we can calculate the value of alpha and alpha. Now, using the boundary condition, what will be the boundary? The boundary condition will be that if you consider first u outer, now consider the radial part of the world very far away from the nucleus. So naturally it will be zero, but very far away from the nucleus, the effect will be zero. In fact, nuclear force it has found that the nuclear force is very short range time. Then you don't have to go to infinity. That means infinity has also a relative in comparison to the range of the nuclear force. This infinity is very small. So outside in fact, we can see that just few times the length of the square will potential, what rectangular potential, the u out dies out. Right? Now, at infinity, u out must be zero. If we want to uh, exploit this boundary condition, then b dash must be right. Otherwise, exponential AR at R equals to infinity will bump. Right? So in order to stop the bump of the wave function at infinity, b dash has to be zero. So we are found E out equal to b exponential AR. And another boundary condition you can say you can guess is the wave function at R equals to zero. Now at R equals to zero, the wave function, that means in the world, the wave function must have to be zero. So if you put r equal to 0, then sine term is 0, cos term is 1. But if you restrict our consideration, e will be equal to 0 at the center. That means if it has no motion, then it will be static in the center. So it will die out. The whole function will die out. Will get part of it. Die out at the center. This was also the case for atomic problem also. Then A dash must. So A dash and B dash, these two constants has to be zero in order to satisfy the boundary condition. And this has been written in this way. Exploiting the boundary condition, U out tends to infinity as R tends to infinity implies B dash equal to zero. And the second boundary condition, U in tends to zero as R tends to zero implies A dash equal to zero. So we are left with two constants. One is constant A and constant B. These can also be given from another boundary condition or another condition, which is at the boundary wall, right? That means that R equals to B. This wave function, that U in and U out, has to be aligned in order to have the continuity, because it's the same wave function, the same particle. One has wave function inside, which is sinusoidal type, and outside it is exponentially decreasing. With these two wave functions at the boundary, that means r equals to b has to be same. So this condition can be mathematically put in this form. Here u dash represents differentiation with respect to r. So u dash in by u in at b evaluated at b and u dash out by u out evaluated at b. These two things, these two values must be same. Now you can perform the differentiation. Now u dash in equals to how much? A k1 cos k1 r and b will be a k1 cos k1 b and u in at b will be equal to a sin k1 b. And if you take the ratio, then it will be k1 cot k1 b. Simple, right? And the second case, since this is exponential form, it will not change. So the only since it is in minus, so the u out dash by u out at b will be equals to minus alpha. Simple, very simple. So left hand side will be k1 cot k1 b and right hand side will be minus alpha. So this is the condition relating k1 and b. Right? This is the condition relating k1 and b. So putting these values, we see that cot k1 b equals to minus alpha by k1. Now if you put the values of alpha and k1, you see that the value alpha was taken at going back. Alpha was taken to be this thing. This alpha is taken to be twice mu a square ed square ed and k1 is this. So alpha by k1, alpha square by k1, so this comes alpha square by k1 equals ed by v0 minus ed because twice mu a square is there both side. So alpha by k1 is equal to root over ed by v0 minus ed. Right? So we are writing it here. So minus ed by there is a negative sign minus ed by v0 minus ed. So this is the equation cos k1b equals to alpha by k1. Right? Now this equation can be solved. There are two unknowns, right? One k1 and another alpha. And this equation is a transcendental form. That means in the right hand side the same right hand side and left hand side the same value of k1 is there. Now how to solve it? There are two methods in which it can be applied. One is numerical method and another is graphical. So we will apply graphical method to solve this equation. But before that, before going into the exact solution of this equation, transcendental equation, let us guess how much the strength of the potential must be. That means we want to find the value of V0. The magnitude of V0 tells us the strength of the force, right? So we are just considering the just bound state. That means ED equals to, we are putting ED equals to 0. It is neither free nor bound, it is just bound state. If putting ED equals to 0, Deuteron binding energy 0, and this is just free or just bound state, then cot K1 is replaced by K0, right? K1 is replaced by K0. Again, I am showing you the relation, the constant values of the constant that I have written K0 or 0 because if it is 0 equal to 0, then K1 goes to is equal to K0. So cot K1 cot K1b K0b will be equal to pi by 2, right? So we know the value of K0. We put the value of K0 into m VOM by h car square, right? K0 is given m VOM by h car square twice mu by h car. So m equals to mu equal to m by 2 into VOM into b square. So actually we are squaring K0 has a value square root. So So k0 value is this and squaring it pi square by 4. So v0 OM will be equals to pi square square by 4 square. Now we know all the values are known except b. H car square is Planck constant. M is the mass of the nucleon, that means the mass of the proton and mass of the neutron. Uh, it is known. And if we assume b to be too far, other experimental evidences for the range of the strong nuclear force have been obtained to be of this order 2 further. That means 2 into 10 to the power minus 15 meter. If we insert these values, I will request you to calculate these values on your own hand. Put the value of h cut. H cut is there, so the h square by twice 4 pi square will go out. There will be 4. This there will be 4, right? So it will be 16. Put the values of m and b will become square. Then we will get the value of 25 m. So the strength of the potential for just bound neutron is very large. 25 into huge amount that we have. This is a huge amount of energy for a just bound of the Gaussian. Next, what we have to consider? Next, we have to consider the actual solution of the problem. That means solving this equation, cot k1b equals to minus alpha by k1. So we are now heading towards the solution. Now coming back to the solution, we have changed the variable cot k1b equal to x, then cot x equal to alpha b by x, right? There are alpha by k1, so k1 will be equals to b by x, right? k1 will be equals to x by b. So b comes out. So minus alpha b by x. Put the value of alpha and b. This is this, and calculating this by, so this will be minus 0.6463 by x. So cot x equal to minus 463 by x. This is the equation we have transferred, and the variable is x. X is nothing but k1b. Now how to solve this equation? To solve this equation is very simple. Plot cot x and plot this thing, and the intersection of these curves will give you the solution. If we plot cot x for various values of x versus minus 460 by x, we will get this solution. This is the minus 1 by 460 by x, and cot x has this type of solutions. This intersection, this and this. So there are many solutions, not only one solution. There are many solutions, and you can see that the solutions there for cot or x values near to 0, cot x values near to 0. Right? So at once we can say that the solution general has this form. Solution has general this form, because you know cot at 0 tends to infinity and at pi tends to infinity. At pi by 2 cot equals to 1. Right? Because at pi by 2, I'm sorry, at pi by 2, it tends to infinity. I'm extremely sorry. At 0, its value is value of cot x. That means cos x by sin x. It is infinity, and at pi, it is also infinity. So it has a value 0 at pi by 2. Pi by 2, value of cot x is 0. Right? So the solution, you see that just above pi by 2, and here also 3, just above 3 pi by 2. So the general solution can be written of this form: x equal to k1b greater than equals to 2n plus 1 pi by 2. For n equals to 0, the first solution, just greater than pi by 2. For n equal to 1, pi by 2. For n equal to 5 by 2. So these are the solutions. The smallest possible value for n equal to 0, which is called the ground state, is equals to pi by 2 plus epsilon. Right? Epsilon 0 is a very small number. Right? This value is very small now. Now, cot k1b, there is a simple trick. Cot k1b equal to cot pi by 2 plus epsilon 0, putting it there, equal to minus tan epsilon 0, because it is going to the second quadrant. Minus tan epsilon 0 equals to minus epsilon 0, since epsilon 0 is very small. So, seen in the solution that it is very near to the pi by 2. Right? So, epsilon 0 is very small. So, cot k1b equals to minus epsilon 0. Therefore, k1b, cot k1b will be equal to 0.463. Right? K1b equals to 1. This is the first exact thing. Now we are putting k1b equals to, pi by 2 plus epsilon 0, and cot k1b equal to epsilon 0. This is approximate. Right? Now if we are putting this thing, then epsilon 0 comes out to be 0.295. Because you know the value of pi by 2. This value is given, so you know the value of epsilon 0. You can calculate it. Do it in your own hand. Pi by 2, put the value of pi by 2. So it will be pi by 2 into epsilon 0 plus epsilon 0 square. Epsilon 0 square is very small, so we can ignore this thing. And so epsilon 0 will be equals to this by pi by 2, right? So this into 2 by pi. If you calculate it, put the value of pi, then it will be minus, sorry, 0.295, right? So the value of epsilon is 0.295. Therefore, K1b equals to, put the value of pi by 2, 1.87. So you know b equals to 2 for me. So K1 equals to this thing, right? 1.87 by 2 for me. Equals to, if you put the value of fermion, then this comes out to this. This comes out to this 0.935 10 to the power minus 15. Now we are putting the value of K1, then and the value of V0 and ED will be 36 MeV, which we have obtained 26 MeV approximately, roughly. The exact value is 36, so this will equal to 38 MeV. So the potential depth NP interaction is very large. Right? Approximate values or rough values are 25 MeV, but the exact value is 38 MeV. So we see that the though deuterium is a very loosely bound state, but the potential in which is it is acting, potential in which, but the potential in the nature of interaction potential between these two nuclei, or in other words, the strength of the strong nuclear force is tremendously high, because it shows the strength of the potential is manifested by the large value of the potential V0. Now it's a very puzzle. Why? The strong potential, having strong interaction potential between neutron and proton, has very so small binding. We'll see that in the case of discussion, why deuterium is a very loosely bound state despite of the tremendous amount of force of the deuterium. So next we have to consider the nature of the wave function, from which we will also extract many important things, but I think today it is enough. I'll discuss it in the next class. So I am just uh, making summary or recapitulate the today's class. First, we have considered the experimental evidences that we obtained about deuterium. We have taken Deuteron as a test nucleus to investigate strong nucleus. So we first see the experimental evidences for deuterium, uh, and combining these experimental evidences with the spin and magnetic moment of the proton and neutron, we see that the deuterium proton and neutron spin are parallel, and for three possible orbital angular momentum or orbital quantum numbers L equal to 0, 1 and 2, the spin 1 of deuterium can be explained. Then we came directly to the Schrodinger equation for the two nucleon system. Therefore, the mass has been replaced by reduced mass, and the potential interaction potential we have taken is the rectangular or square wave path in order to simplify the problem. And separating in order to solve the Schrodinger equation, we have separated the radial and angular part as usual, and taking solutions eigenvalues of the angular part to the orbital angular momentum L into over L into L plus 1. We have inserted this value in the radial part, and the radial part of the wave equation for the deuterium comes out to be this. And we further simplify this equation by considering the ground state, that is L equal to 0, so that centrifugal potential term analysis, and we have two solutions, one for inside and for outside. And these two solutions, when matched with the boundary condition, that they will be and the solution of these two equations were of this form, and out of the four integration constants, two of the constants have been eliminated by choosing the boundary condition, and additionally we get another equation relating k1 and alpha by seeking the continuity of the two equations, radial for the equations, two equations u in and u out, and from which we see that for just bound state, for the deuterium, the potential square wave potential must be very large of 25 eV. Then we proceed to solve the equation relating k1 and alpha. Exactly, that means with graphical solutions, and from using the graphical solutions, we found that the value of the potential is actually 38 eV. This is very large. In spite of the very large interaction between the proton and neutron inside the nucleus, deuterium binding energy goes on. This is a puzzle where we solve this, or we will investigate this thing in the preceding classes, next classes, uh, and the nature of the wave function have actually also has to be investigated, because it will give much more information about the nature of interaction, nature of nuclear, strong nuclear interactions, and we'll also see that why L equals to 0, out of L equal to 0, L equal to 1, and L equal to 2 possible values of orbital quantum number. Only L equal to 0 in bound state, other unbound state will not. So today up to this. Thank you everybody.